In this video, we're going to continue our discussion on derivatives by learning another rule for differentiation. It's called the chain rule. And the chain rule is used to differentiate a composition of functions. So let's just write down our rule to begin with. It says that if f of x, capital F of x, is equal to f composed with g of x, which is f of g of x, then the derivative of capital F is equal to little f prime of g of x times g prime of x. And the way I like to remember this rule is it's the derivative of the outside function times the derivative of the inside function. I'll explain that more when we get to an example to make it a little easier to see. And I'm going to also quickly write down our other notation in case you prefer the other notation for derivatives. So the other definition of the chain rule, which is equivalent, it's just using our other notation, says if y is a function of u and u is a function of x, then the derivative of y with respect to x is equal to the derivative of y with respect to u times the derivative of u with respect to x. And this is still the same thing. It's the derivative of the outside function times the derivative of the inside function. So the best way to learn chain rule is just to do a lot of examples. So let's start with a fairly basic example. So we are going to differentiate the function f of x equals square root of x squared plus 1. And the very first thing I'm going to do is something I almost always do in calculus, is rewrite my root as an exponent. So the first thing I'm going to do is rewrite this as capital F of x equals x squared plus 1 in parentheses to the 1/2 power. So now we have to figure out what is this outside function and what is this inside function that we're thinking about. Well, by the outside function, I'll write that in red. The outside function is what I get when I kind of ignore what's in the parentheses. My outside function is something to the 1/2 power. And we know how to do that derivative using a power rule. And then my inside function is the stuff inside the parentheses, x squared plus 1. So if I'm going to do this derivative with my chain rule says that I should have the derivative of the outside function times the derivative of the inside function. Now, the derivative of the outside function, my 1/2 would come down. I would still have whatever was there in parentheses, and my new power would be negative 1/2. And multiplying by the derivative of the inside function would be multiplying by 2x. So the only thing I'm missing right now is that I do need to have something in those parentheses. The something that's in those parentheses is exactly what was in the parentheses before. So the way the chain rule works is if you have a set of parentheses like this, you kind of ignore what's in the parentheses for a second, do your power rule, make sure you fill the parentheses back in, and then multiply by the derivative of that stuff that was in the parentheses. And then this we can simplify a little bit because 1/2 times that 2x would just get me x. So there's a couple ways we could write our answer. We could say f prime is equal to x times x squared plus 1 to the negative 1/2 power. Or if you like rewriting back with roots and putting negative exponents in the denominator, it'd be x over square root of x squared plus 1. So that's our first chain rule example. It's not too terrible, but now we can, as you can see, we can start doing derivatives of more and more complicated functions. Let's do another example. Differentiate y equals sine of x squared and y equals sine squared of x. So these look like very similar functions, but the outside function and the inside function are different on both of these. So let's take care of this guy first. Y equals sine of x squared. When y is equal to sine of x squared, this means that my outside function is going to be sine of something. And the inside function is going to be what was inside the parentheses, x squared. So this means that y prime is equal to the derivative of the outside function. Derivative of sine is cosine. So I get cosine of, same stuff that was there before, times the derivative of the inside function. So times 2x. And that's my answer, though we would more commonly write it as 2x cosine of x squared. Not too terrible. One of the most common mistakes I see with chain rule is students will want to take the derivative of sine to get cosine and take the derivative of x squared to get 2x, but rather than multiplying by that 2x, they put the 2x inside the parentheses there. So make sure you're doing two separate derivatives and they're being multiplied together. Let's do the other one, y equals sine squared of x. So for y equals sine squared of x, I'm just going to emphasize this is the same thing as y equals sine of x squared. And I'm rewriting it that way just to really emphasize which thing is the outside and which is the inside. For this function, the outside is going to be something squared, and the inside is sine of x. So when I do the derivative of the outside function uses a power rule. The 2 comes down, you still have the stuff in the parentheses, and the new power is 1. And the stuff that was inside the parentheses was sine of x. Now this has to get multiplied by the derivative of the inside function. The derivative of sine is cosine. So I get 2 sine x times cosine x. Notice that it did matter what order these functions were composed in. My answer for one order of the composition is completely different than the answer for the other order of composition. So you have to make sure that you are specifically doing the chain rule for the appropriate composition of functions. Let's do another one. Basically, the rest of this video is just going to be tons of examples, all chain rule examples, just to give us a lot of practice. So let's do differentiate y equals x to the third minus 1 to the 100 power. So to do this one with the chain rule, the outside function is something to the 100th power, and the inside function is x to the third minus 1. So the derivative is going to be the derivative of the outside. That's where my 100 comes down and my new power is 1 smaller. Don't forget to fill in your parentheses. This is the derivative of the outside. And then I have to multiply by the derivative of the inside. In the derivative of the inside, I get to use the power rule again and get 3x squared. This is the derivative of the inside function. And all I can really do to simplify this is notice that the 100 times the 3 gets me 300. And I'm going to write the x squared in the front. You don't need to, but it looks a little better in the front. And I get y prime is 300x squared times x cubed minus 1 to the 99th power. All right, another one. Let's differentiate the function f of x equals 1 over a cube root of x squared plus x plus 1. And now the very first thing I would do is rewrite this so that the root is a fractional power, and also rewrite it with a negative exponent to get that out of the denominator. So if I rewrite this, I will get that my function is equal to x squared plus x plus 1 to the negative 1/3 power. And now it's a little easier to see the outside and the inside function to do our chain rule. So the derivative of the outside function, I have something to the negative 1/3 power. So the negative 1/3 comes down, and my new power is 1 smaller. Negative 1/3 minus 1 is negative 4/3. And then don't forget to fill your parentheses back in. Now this whole thing needs to be multiplied by the derivative of the inside function. So the derivative of x squared plus x plus 1. Well, that would be a 2x, and the derivative of x is 1, so I get 2x plus 1. And that is the answer. Again, if you really want to, you can simplify by rewriting, by putting the negative exponent back in the denominator and all of that. I personally wouldn't. I would just leave my answer right here. It's a correct answer. But if you're told to simplify, then you probably should rewrite it without a negative exponent. All right. So now I think we are ready for a more complicated problem. We've done a few examples of chain rule now. It's probably starting to feel a little okay. But now guess what? All of those rules we learned before, our product rule, our quotient rule, you can have those in combination with the chain rule. So we're going to do one of those examples. These can get really complicated really quick. Let's differentiate the function g of t equals t minus 2 over 2t plus 1 to the 9th power. So this is a chain rule problem because I have a bunch of stuff in parentheses to a power. The derivative of the outside, I'll have the 9 come down and my new power be an 8. But the derivative of the inside function, my inside function is a quotient, so we're going to have to use the quotient rule to do that part. I hope you're ready. This one's going to be a little more complicated. All right, chain rule says that we need the derivative of the outside function. That is 9 times the same stuff in the parentheses to 1 power smaller, so an 8th power. Now this whole thing is the derivative of the outside. I need to multiply this by the derivative of the inside function, which is going to be a quotient rule problem. Our quotient rule, remember, is the low d high minus high d low, square the bottom, and away we go. So for the low, we have 2t plus 1, d high minus my high, which is t minus 2, d low, square the bottom, and away we go. And let's fill in those parentheses. D high is the derivative of t minus 2. That is just 1. And d low is the derivative of 2t plus 1, and that just gets me 2. This is the derivative of the inside function, and it's kind of a mess. But that's okay. This technically is the answer. So if you don't have to simplify it, you could leave it right here. I'm going to go ahead and simplify it just a little bit more. To simplify it, I'm going to work with this derivative of the inside function, take care of distributing and combining like terms across the top. So when I do that, we have our 9t minus 2 over 2t plus 1 to the 8th times, I would have 2t plus 1 minus 2t plus 4 all over that denominator squared. So that numerator simplifies to just 5. So we get this derivative is 9 times t minus 2 over 2t plus 1 to the 8th times 5 over 2t plus 1 squared. And we can actually simplify this a little bit further. We could multiply the 9 and the 5 together to get a 45. And then I can rewrite this stuff as a t minus 2 to the 8th over a 2t plus 1 to the 8th. And I still have a 2t plus 1 squared down here. And the only reason I'm doing that is to make it very obvious that I can multiply these two fractions together and end up with a 2t plus 1 to the 10th power in that denominator. So fully simplified as far as it can get, we're going to have 45 times t minus 2 to the 8th all over 2t plus 1 to the 10th power. And that's the simplified version, and it's still kind of a mess, which is why I tend to not bother to simplify my answers unless I really have to, or unless I have to use it later in the problem. Because sometimes simplifying is a lot of work, but it doesn't really make it any more simple. This one, I guess, is a little bit better after it's simplified. So that was a good example of doing a chain rule that also had a quotient rule. Our next example is going to be a chain rule that also uses the product rule. So let's differentiate y equals 2x plus 1 to the 5th times x to the 3rd minus x plus 1 to the 4th. All right, so the first thing I want to point out is this is definitely a product rule problem because I have the product of this guy and this guy. But the problem is when I have to take the derivative of each of those pieces for my product rule, both of those derivatives involve a chain rule. So this problem is a product rule problem that also has two chain rules involved. And that's okay, we just take it one step at a time. So my product rule says that the derivative is equal to the first guy times the derivative of the second guy. which I'll put right there, plus the second guy times the derivative of the first guy. And so now we just have to fill in the derivatives of those two pieces, but they both use the chain rule. So let's start by doing the derivative of this second guy using my chain rule. I have something to the fourth power. So the derivative of the outside function, my 4 comes down, and my new power is 3. And I need to multiply that by the derivative of the inside function. So that's multiplying by 3x squared minus 1. Pretty nasty, right? Yeah. All right, that is the derivative of that one underlined in green. Now we have to do the one underlined in red and put it here. This is another chain rule. Derivative of the outside function, my 5 comes down. My new power is 1 smaller, and I have to multiply by the derivative of the inside, which is just 2. This technically is the answer. Can it simplify? Well, it can. It's still going to be pretty ugly at the very end. I personally would leave my answer just like this. Maybe I would multiply the 5 and the 2 together, just to make it a 10, make it a little simpler. But honestly, this right here is what I would do unless I was told I had to simplify it. So I'm just going to box that answer up. If you are curious and want to find the simplified version and want to know if you got it right, if you want to practice your algebra skills and find the simplified version of this answer, you should be able to get this simplified to 2 times 2x plus 1 to the 4th times x to the 3rd minus x plus 1 to the 3rd times 17x to the 3rd plus 6x squared minus 9x plus 3. So if you really want to try to simplify this, see if you can get that answer. If you have questions on how to simplify it, you can ask them below and I can try to help. Or you guys can email me or come to office hours if you really want to practice that algebra. But the whole point of this video is getting the calculus done. So that's what we did here in the box. All right, so we have done a couple problems now where we had a chain rule with a quotient rule, and then this last one had a product rule with a couple of chain rules. Do you think we can ever have more than one chain rule nested inside of another chain rule? And the answer to that is yes. Our next example is going to be a nested chain rule. So we're going to find f prime, and f of x is equal to sine of cosine of tangent of x. I need more parentheses than that. There we go. So this one is a nested chain rule because right now my very outside function is sine of something. And then the inside function would be cosine of tangent, but I need a chain rule to do that derivative too. My second outside function is cosine of something, and the very inside is tangent of x. So this is just taking it step by step. The derivative of the very outsidemost function, I have sine of a mess. Derivative of sine is cosine. So my very first part is going to be cosine of all of that mess. This is the derivative of the most outside function, outside number 1. I have to multiply this by the derivative of the inside function. Well, the derivative of the inside function is the derivative of cosine of tangent. Well, the derivative of cosine is negative sine, and I need to have the tangent as an input. And then I have to multiply that by the derivative of tangent, which is secant squared. Now, that's kind of hard to read like that, so let me actually rewrite this so I can write it all on one line for you, make it a little easier to look at. So my derivative, we said, was cosine of all of that stuff. That was the derivative of the most outside function. And then I have to multiply it by the derivative of the inside function. Derivative of cosine is negative sine. And the derivative of tangent is secant squared. So all of this is the derivative of the inside function, but I had to do a chain rule to do that. This piece here was outside number 2. And the secant squared was the derivative of inside number 2, which was the most inside function. So when you're doing chain rule and you have a lot of things nested together, you just have to work from the very, very outside all the way to the inside. Just keep multiplying by derivatives until you're as inside as you possibly can get. That right there is the answer. And honestly, there's not really anything you can do to really simplify that. You could put the negative in the very front, but that's about it for simplifying. Let's do another nested chain rule, just to get a little extra practice. Find y prime if y equals the square root of secant of x to the third. So I'm going to do the very first step that I always do, which is rewrite a square root as a fractional power, a 1/2 power. So this is another nested chain rule. The very outside function is something to the 1/2. The next outsidemost function is secant of something. And then the very, very inside function is x to the third. So when we do our derivatives, we have to work from the very outside all the way to the very inside. The derivative of something to the 1/2 power is 1/2 times that something to the negative 1/2 power. Now I move to the next function. Derivative of secant is secant of something times tangent of something. So I get secant of x cubed times tangent of x cubed. And then I multiply by the derivative of the next function. Derivative of x cubed is 3x squared. And there we go. We could try to simplify this. I, again, personally would not really do much. Really, all you can do is we have a secant of x cubed to the negative 1/2 and a secant of x cubed to the first. You multiply those together and you get a secant of x cubed to the 1/2 power. So we might want to do that. So about as simplified as it can get. Let me put the 3/2 in the front. I have my x squared. My secant of x cubed is to the 1/2 power when I combine them together. And then I have a tangent of x cubed. But that's about as good as it's going to get, and it's still pretty ugly. It's okay to get ugly answers. We are in calculus now. Not all of our answers are going to be super pretty all the time. You just got to get used to that and not think that that means you messed up. Just think it might mean that the problem's a little bit ugly, and that's okay. All right, that's all I have for you on the chain rule. It takes a lot of practice to get used to the chain rule, but it is a very powerful rule, and it's a good one to thoroughly understand. So I hope you got enough practice in on this video. If you have questions, drop them below. Or you can email me or come to office hours if you're one of my current students, and I will see you in the next video where we do a slightly different version of the chain rule, something called implicit differentiation. So stay tuned.